Hey everyone. So I was teaching diffraction gratings this year when a student asked me an excellent question. It was about a slide I'd made where there was a diffraction grating with an odd number of slits, and I'd claimed that if the path difference from each of the slits to the screen was a half wavelength apart from each other, that would ensure destructive interference at the screen like in a double slit. But then they brought up an excellent point, which is that won't pairs of slits cancel out with each other, leaving the contribution of the last slit, since there's an odd number of slits here? So you'd never really get destructive interference this way. And this was such a good point, and I had never really thought about it before, so I gave something hand wavy. But afterwards, I got to thinking, and I realized that there was just so many things about diffraction gratings I straight up didn't understand, or had never bothered to think through, or just given up along the way, because it's a topic that is so poorly explained and covered in textbooks and websites and stuff. And I think what followed was just such a fulfilling journey of discovery that I really wanted to share it with you guys. So I'd like to bring you along with me on that same journey. So what that would look like is this, but first I want us to first motivate why we'll need some new techniques that we've never quite seen before in order to approach this problem. So I want to start where I started, which is with the next hardest problem from the double slits, which is the 3-slit interference problem. So deduce the interference pattern when light is incident on 3 slits rather than 2. So this is the problem that I want to solve, and we'll start with thinking about where the maxima are going to sit. Well, the obvious one would be the central maximum. If I look at the paths from each of the slits to the center of the screen, then because they have no path difference to each other, I should expect a bright maximum right in the center, same as in double slits. Similarly, if the path difference between adjacent slits is 1 wavelength apart, I should expect another maximum there. We can call that the first order maximum. Same physics, right, as this double slit. Now actually for today, instead of seeing the path difference to the screen in this very visual way that's very close to the apparatus, I want us to abstract it a little bit and actually think more carefully about each of the waves that are actually sitting in each of these paths. And this will be more relevant for what we're going to do today, and it's also just more meaningful, it's more closer to the real physics of what's going on. So that's to say that instead of thinking about each of these paths as being straight lines in 2-dimensional space, I want us to draw out each of the actual waves, making them up. And I want to lay them out flat in 1D to reduce this 2-dimensional problem into a much simpler, analogous 1D problem. And what we see here is the reason why, so I think what this drives home is the reason why we get constructive interference even when there's a path difference of 1 wavelength is because the 1 wavelength preserves the phase between adjacent contributions. So you can see that we can shift this wave to the right 1 wavelength, and yet it still remains in phase due to the periodic nature of waves. Waves repeat after a single wavelength, so it doesn't matter whether we shifted it to the right 1 wavelength and we shifted this to the right 1 wavelength. We might as well have just shifted this one to the right by another wavelength, like this, and then the next one by another wavelength, like this. We can keep shifting by as many wavelengths as we want, and as long as we do this, we'll always get constructive interference. So what we see then is that our classic condition of the path difference, of constructive interference occurring when the path difference is an integer multiple of wavelengths, we see that still holds no matter the number of slits. So that's always true. I guess just to make sure we're on the same page here, is it possible for the first 2 slits to have a path difference of, let's say, 2 lambda, but then the next 2 slits have a path difference of something else, say lambda? Would you still get constructive interference this way? Well, yes, you would, because all the waves will be in phase, but the problem with that would be, it's literally impossible. And, nothing about this diagram here would tell us that it's impossible, but what tells us it's impossible is the actual geometry of the apparatus. And so, yeah, even though I want us to abstract away what's going on here, I think it's important that we always remember that what we're talking about is this setup here, where the path difference between the first 2 slits determines the path difference between or further slits to come. That is to say, I can't have a path difference here and a different path difference between the next two slits. That is not going to be possible. So for the rest of today, I'm not going to draw this diagram, but if you ever get confused, I would recommend going back to this diagram and thinking about what's actually going on with the actual apparatus, okay? Excellent. Okay, now let's consider destructive interference. So, like I mentioned, the most natural thing to do would be to do the same thing as what we do in double slits, which is to consider a path difference of half a wavelength, to which the first two slits, they'd cancel out, giving you nothing, but then that just leaves the contribution of the third slit, and so, this isn't perfect destructive interference. And so I guess the problem that I was thinking of then is it even possible for three waves to perfectly cancel out? And so I went on Desmos and I sort of played around with the phase shifts and I played around, and then I realized something which in retrospect is quite obvious. Yes, three waves can absolutely cancel, and this occurs when their path difference is a third of the wavelength. So in Desmos, this is what I saw, and indeed, when you do this, when the path difference is a third of a wavelength, you can add all the graphs up and you'll just get a straight line at 0. And so this is all nice, this is all well and good, but I guess another question would be, is there any other path difference that I can use that will still get me the same thing, that will still get me destructive interference? What about for like an n number of slits, where we have not just 3 but n slits? Can we create some sort of empirical law that can be generalized to be true for any number of slits? And I guess what we see here, and the reason why I wanted to show, the reason for this section, I suppose, is that this problem is tricky. It's difficult to add sine graphs together unless you're in Desmos. What we need a new systematic tool that can be scalable to any n number of slits. And once we have this tool, we can solve this problem with ease. And that is the motivation for the next section, for phasors. And what a phasor is it's a graphical representation of a wave. So for instance, if I've got a wave as shown on the right, then the phasor will be the rotating vector shown on the left. Now if I pause this in some moment of time, t, like when we draw phasors in this way, if we draw it on the page, we can't actually draw it rotating, of course. We always draw it at some moment in time. And so I pause this animation at some time t, and let's say at this time t, that means that we swept out an angle omega t at this time instead. But remember, we should always remember that what this is it's a vector rotating about the origin at some angular speed omega. Okay, and let's say that the sine wave on the right is some electric field, some oscillating electric field with the equation E0 sine omega t. So what this means then is the amplitude of the wave, and thus the amplitude of the vector, is E0. Then the wave itself is going to be the projection of this vector onto the vertical axis. So this vector over here. You can see this really clearly in the animation. If we look at what's happening in the vertical axis, you see this particle oscillating back and forth, up and down. And critically, if we graph out its displacement time graph, then that is the actual wave itself. That is what we see on the right-hand side. Okay, so that's the relation between phasors and waves. A wave is the vertical projection of the phasor. Okay, so let's try to solve a problem now. I want us to consider the wave E1, which has the exact same equation as before, and I'll plot it on the phasor diagram. And I want us to consider another wave E2, but this wave has a relative phase difference of phi to the first wave. And critically, it also has the same angular frequency, and in all the problems that we're going to do using this method of phasors, we have to assume that all of the waves that we're working with are going to have the same angular frequency. Otherwise, we can't plot it on the same phasor diagram, because there's really no way, other than through an animation, to show that the phasors are rotating at different frequencies, right? And so we have to assume here that they're of the same frequency, and this way I can plot it on the same diagram as shown. So then I want to ask you, how can we do E1 plus E2? How can we add these two contributions together? Well, doing this algebraically is quite a tricky task. If I ask you to add E0 sine omega t with E0 sine omega t plus phi, how would you even do that? How would you express it as a single clean sinusoid? It's quite a tricky task. You probably need to use some trigonometry trick. I'm not really sure what to do because I don't know, I'm not that good at maths. But by representing them as phasors, we've just turned this algebraic problem that requires tricky trigonometry into a vector addition. That is to say, what the problem is now this. And so we can add these vectors together, and the resultant vector is this. And critically, even though these two vectors are rotating around, and that means that this resultant vector, the resultant wave, is actually going to be the projection of the y-axis as this black vector rotates around, what we notice is that the magnitude of the resultant vector stays the same. This purple and this orange rotate around, but they maintain the length of the black vector. And actually, the reason why I bring this up is because even though the projection of this vector is the actual wave itself, which is a time-varying wave, when we talk about interference patterns, as we will later, we don't actually care about the time-varying wave. We don't care about the projection. What we care about is the intensity of the wave, which is the time-averaged value of the wave. So you can essentially think of that as being given by the amplitude of the wave, which is given by the black vector. So in other words, we don't really care for the fact that there is some starting phase of omega t. We don't actually care. We could have started at any time we wanted. We could have paused the animation at any time we wanted. We could have paused the animation at such a time t seconds ago, such that the first vector is perfectly horizontal. And so in all the phasor diagrams that I'm going to draw today, I'm going to assume that the first vector is horizontal. But critically, it doesn't matter because both of these vectors are rotating. So I could have just stopped it at any instant in time and stopped it there, and then the first phasor would be at a different angle to the horizontal. Okay, so I think at this point I need to address something, which is that I've been drawing these vectors in some sort of abstract plane or space. So I think you might be wondering what these axes actually are. And in fact, if you do 4-unit maths in high school and you've worked with complex numbers, you may have already pieced together what's going on, which is really what we're doing is we're representing a wave as the vertical projection of a vector that sits in some plane. And this is exactly analogous to how we take the imaginary part of a complex number that sits in the complex plane to represent waves. And so when we're actually working with the maths of phasors, we don't actually want to sort of draw out the phasors and add them up geometrically. This is quite a tricky thing to do. And so we won't necessarily need to work with the maths today. We just need to work geometrically with the vectors. But in some situations, we do want to work with the maths. An example of this is, for an example, in electrical engineering. We often work in electrical engineering. A big problem that we're trying to solve is how to deal with complex circuits with AC signals. That is to say, if in different parts of the circuit we have these sinusoids that we're generating with our power sources, and then these power sources, they respond to different elements in the circuit, which causes us to multiply and add each of the sinusoids together, and somehow we need to express the final result as a nice clean sinusoid. And so what we need is a systematic way to do this, and phasors is the perfect solution. If we represent a phasor as a complex number, then complex numbers lend themselves really well to being added in Cartesian form or multiplied in polar form. And never once do you actually have to think about the geometry of sort of adding vectors. It's abstracted away from that, and you just have to work with maths, and right out of the maths pops out the final result. And this is exactly what we'll do in electrical engineering. But of course, we won't need to work with any maths today. We'll just need to work with the phasors geometrically. But yeah, this is really where this technique is most commonly used and is the most prominent. But as for our case, we need to bring it back to the physics. And so I want us to ask, can we use phasors to go back to the double slit interference pattern to explain what's going on with this new framework? So what happens for the central maximum? Well, we know that this happens when there's no path difference between each of the light emerging from each slit. But when talking about phasors, we don't care about path difference, we care about phase difference. That's what we're representing with the phasors, right? So what does no path difference mean for the phase? What this means is no phase difference. So we'll just keep these vectors as they are and just add them head to tail, as shown. Okay, what about the first order maximum? Well, we know that this occurs when the path difference is one wavelength. And so what this is analogous to is, well, how do we convert one wavelength into a phase? Well, we know that one wavelength is 360 degrees. So if we rotate the second phasor by 360 degrees, then we get the first order maximum. I mean, it's kind of just obvious seeing it this way because rotating the vector 360 degrees does nothing to the phasor diagram. This phasor diagram is exactly the same as the last one we just saw. And so we can multiply by any multiple of 360 degrees that we want. We'll always get the same diagram. And so we're always going to get constructive interference this way. Okay, what about the first order minimum? Well, we know that this occurs when the waves are perfectly out of phase, which is a phase shift of 180 degrees. In other words, if the second phasor is rotated 180 degrees to the first, you should expect destructive interference. And with the phasors, this kind of just makes sense. If you add two vectors in this way, they should perfectly cancel out. Okay, so summary slide here. We can see the central maximum is when you just add the phasors unaffected head to tail, and then the first minimum occurs when the second phasor is rotated 180 degrees relative to the first, and then rotating through even more by another 180 degrees, you get that we get the first order maximum. Okay, and critically, we have a path difference here. We have that the first order maximum is when there's no path difference. The first order minimum is when you get half a wavelength of path difference. But critically, when we talk about phasors, we care about converting to the analogous phase difference. So 0 degrees, 180 degrees, 360 degrees, so on. And then for the left-hand side, it's exactly the same as the right-hand side due to the symmetry. Okay, so I think we're ready now to talk about 3-slits. And I trust now that you're starting to get the idea of phasors. So I'm going to begin abstracting away the phasors from the actual waves that they're representing. But I would really highly advocate that if at any point you get confused at what's going on with the phasors, that you draw the waves back. You consider the apparatus again and you bring it back into context. But I'm not going to do this for the rest of this lecture. Okay, so I want to start with the double slit interference pattern, and just so that, and what I want to do is I want to sort of graph the 3-slit interference pattern on top of this, but if I did it like this, it wouldn't fit on the page, and so I want to just consider the right-hand side of this graph, and then the left-hand side. You can just imagine it, it's going to be exactly the same, just flipped. It's symmetric about the vertical axis, right? So let me get rid of the left-hand side and zoom in. Okay, so where are the maxima? Well, I know that the central maximum, once again, occurs when there's no path difference. So, this is no phase difference. So if we consider the phasors from each of the slits, what this looks like is just adding them up head to tail with no relative phase. And so that's going to give us our central maximum. What about the first order maximum? Well, we mentioned this earlier. If each of them has one wavelength of path difference relative to each other, which corresponds to a 360 degrees phase difference, then we'll get the first order maximum. And what that looks like is rotating each of the vectors as so. So they have a 360 degrees phase difference to each other, and that gives us this. Okay, so what we see then is that no matter the number of slits, we'll always get maxima at m lambda. So path difference equals m lambda is still the condition for constructive interference in any number of slits. And so the funky case is for the minima. I want us to first start with so we can consider, the most obvious case, which is what happens for the double slits, which is when the path difference is half a wavelength. So we can try this, but it won't work out as we discussed at the beginning of the lecture, since two contributions cancel out, leaving the third. And so what we'll do is we'll slowly rotate the vectors until we get that each of the vectors add in such a way that they perfectly cancel out. And what we'll get is this. And so adding all of these vectors head to tail, we'll get this. And this leads us to all three vectors perfectly cancelling out to give us the first minimum. Okay, let's rotate a bit more. And this is our classic case of what happens when each of the slits has half a wavelength of path difference from each other. So what we see then is that the first two slits cancel out, leaving only the contribution due to the third. And when this happens, when the contribution at the screen is only due to a single slit, we call this a secondary maximum. And so what the maximum will look like is something like this. And critically, this is just due to 1/3 of the total electric field contribution. Okay, so what we see here is that the secondary maximum occurs when the path difference is half a wavelength apart. And we know that half a wavelength apart, this is where the first order minimum in the double slit interference pattern sits. And so what we found is actually quite an interesting result, which we're going to have to use later on, which is that secondary maxima, they seem to sit on top of the minima of the previous slits interference pattern. And so in the double slit interference pattern, wherever the minima is going to be a secondary maximum in the 3-slit interference pattern. Okay, so now let's rotate even further. Oh, and look, we get an A for Atlas, and adding these vectors head to tail, we get an upside down triangle. We get that the phasors perfectly cancel out to give us the second minimum. Okay, and so summary of all of this, we see that for the central maximum, we add all of the vectors with no phase difference head to tail, and then rotating a little bit with 120 degrees phase difference, we get that the phasors form a triangle that perfectly cancels out. Rotate even more, such that the phasors have a relative phase difference of 180 degrees. They look like this, and this gives us our secondary maximum, where the first two slit contributions cancel out, leaving the contribution of the third. And then rotate even further to 240 degrees, we get something that looks like this, which perfectly cancels out to give us the just destructive minimum. And then here we lay them out flat to give us the first order maximum. So there are a couple of things to note here. The first is that the electric field contribution of the secondary maximum is 1/3 of the total electric field emitted from the source. And so the intensity should be 1/9 of the total intensity from the source, or the intensity of the central maximum, because the intensity is proportional to the electric field squared. Now I haven't really drawn this properly here, like this is not really 1/9 of the central maximum, but I've had to exaggerate it, otherwise very quickly as we add more slits, it will very quickly get small and eventually we'll be able to see nothing. So I need to make sure it's nice and big for you to see. That's the first note. The second note is that you'll notice that I've drawn it in such a way that the maxima sit at the same spot. And remember, this is only true if the distance between the slits stays the same. So if my 2-slit interference pattern looked like this, then when I add the third slit, I'm maintaining the distance between the slits such that the distance between the slits is the same. But if I do this, then I'm literally allowing more light through. And so what I should expect is that the intensity has increased when I add another slit. Same for any further amount of slits. But critically, because the intensity increases at an increasing rate, like I wouldn't be able to fit the subsequent slit interference patterns on the same graph, and it would very quickly sort of leave the page. And so I've sort of normalized the graphs here such that all of the graphs that I'm going to draw in the rest of the lecture will have a normalized intensity, the same intensity. Okay, so the maxima, like I mentioned before, they follow the same relation. The path difference is equal to an integer multiple of the wavelength. They follow the same condition. The condition for the minima is slightly funkier. So I've converted each of the phase differences here into the corresponding path difference. And so I want to ask you the question, looking at the path difference, can you think of a new empirical law for the geometric condition for when we get minima? And then can you generalize this to any n number of slits? So I would really advocate that you pause the video to have a think about this. So remembering that the condition for constructive interference is this, when the path difference is an integer multiple of wavelengths. And we just proved that this is true no matter the number of slits. Right? This is always true. Okay, so I'm going to show you the relation. It turns out that for destructive interference, it can be shown that the condition is given by the path difference is equal to k on n lambda. You can see this to be true. Right? If k is some random integer and n is the number of slits, then you can see that this is 1/3 of a wavelength, and then this is just another integer divided by 3 times the wavelength. And so critically, what we see is that this equation pops right out of the geometry of what's going on. So where k is some random integer and n is the number of slits. But there is a caveat here, which is that if you notice, if we keep going one further, so we increase the integer from 2 to 3, then we end up with 1 lambda, which is the condition for constructive interference. And so what we see is that when k on n is equal to some integer, say m, then what we get is that this condition here collapses into the condition for constructive interference. And so we have to make sure that if this is purely a geometric condition for destructive interference, that we place a restriction. And that restriction is that k on n isn't equal to some integer. Okay, so let me ask you now, how many minima should there be between principal maxima? How many should we expect? Well, what you should be able to derive for yourself is that there are n-1 minima in between maxima. And the way you can think about this is that given this relation here, what we see is that there are n-1 fractions until you get to the next whole number and you get to the next maximum. And so what this means is there should be n-1 minima. And we look at the graph, this is consistent, right? So here we have n equals 3, there's 3 slits, and so we should expect 2 minima, which is consistent. Okay, so what I'm going to do is I'm going to give the x-axis a label now, k, and so I'm going to plot k on the x-axis, and this is really neat. If I plot k equals 0, 1, 2, 3, then I can sub this into the equation, where if k on n is not equal to an integer, then I get destructive interference. I'll color code this with purple. And then if k on n gives me an integer, say 0 or 1, then I'll get constructive interference, which I've color coded as orange. Can you think of the condition for the secondary maximum? Well, we just said that secondary maxima sit on the previous slit's interference pattern. So if the previous slit number is n but minus 1, so the current number of slits minus 1, then what we're saying then is that if the path difference is equal to the exact same thing before, but where n is equal to n-1 now, then we'll get the condition for the secondary maxima. Once again, if k on n-1 is equal to an integer, then this collapses to the condition for constructive interference, so that's no good. Okay, let me ask the same question now. How many secondary maxima should we expect between principal maxima? Well, what we should expect is that there is a secondary maximum. If this is a nice, well-behaved function, then what we should expect is that with every minimum, it should rise to a secondary maximum. If it's nice and continuous. This is something that is quite intuitive, right? And so if we're saying that there are n-1 minima between principal maxima in every interference pattern, then what we should expect is that, well, there are n-1 minima, so there should be one less secondary maxima from that. That is to say that we expect n-2 secondary maxima in between principal maxima. Another way you can think about this is that we said that secondary maxima sit on the minima of the previous slit's interference pattern, and the previous number of slits, and we just said that there are n-1 minima for a given n. So if we take the number of slits that we currently have, so let's say n, subtract 1 to get the previous slit number, and then if we subtract another one from that to get the number of minima, then what we get is the number of secondary maxima of the current number of slits n. Okay, so another way to think about it is n-1 minus 1. Okay, so I'm going to color code the secondary maxima to be a lighter orange because it's less intense than the principal maxima. Okay, so I think we have enough physics now to approach what happens when we increase the number of slits even further. But first I want to recast the 3-slit problem a little bit. You can see I've sort of laid it out a bit different. And the reason why I've done this is because I don't want you to think of the condition for the secondary maxima as being on equal footing with the maxima and the minima. Critically, if you recall, the maxima and the minima follow the geometric condition k on n lambda. The path difference is equal to k on n lambda. It's just that when k on n is equal to an integer, this collapses into the condition for constructive interference. And so really, if I'm plotting k on the x-axis, it's really nice that if I have k equals 0, 1, 2, 3, I can just sub it into the same equation, k on n lambda, to get the resulting maxima and minima coming straight out, right? Critically, this isn't true for the secondary maximum. It's slightly different because remember, the secondary maximum sits on top of the minima of the previous slits interference pattern. And so this k here is different in nature to the k that we're going to use in the top here. And so I've sort of separated it a little bit. It's sort of like the k from the previous from the previous n. Right. Okay. So with that being said, we can start to think about the four-slit interference pattern. But before I do that, I would really highly advocate that you pause the video and try to draw out the phasor diagrams for yourself. You know, we have this geometric condition now that the path difference is equal to k on n lambda. So can you use this to figure out what the phasor diagram should look like? Okay, so I'm going to show you now. It's this. So for the central maximum, you get, once again, it's that classic thing where we add all the phasors head to tail with no phase difference relative to each other. And then if we sub in k equals 1 into k on n lambda, we get the geometric condition that we will get the first minimum at when the path difference is a quarter of a wavelength, or 90 degrees phase difference. And with this gives us a square phasor diagram, where all the phasors perfectly cancel out to give us the first minimum. Rotating even further to 180 degrees, you get the next minimum where all the phasors have a relative phase difference of 180 degrees. And so adding them head to tail, they all cancel out. Rotate them even further, 270 degrees, you get a square in the other direction. And then rotate it even further to 360 degrees, you get the classic thing, the same thing as what we started with. And critically this time, we do get a minimum at half of a wavelength of path difference. This wasn't true, remember, for 3 slits, because when this was the case, 2 slits would cancel out, leaving the third. But when we have an even number of slits, we can pair adjacent slits together such that they cancel out, and so that leaves the final slit. There is no final slit to be left over. We can perfectly we can perfectly create pairs between each of the slits because there's an even number of them. Okay. So that is to say that our old condition for the double slit, for destructive interference, which is an integer plus a half multiple of wavelengths, this works every single time we have an even number of slits. It just doesn't work for an odd number of slits because we can't pair, because we can't create pairs between adjacent slits such that they all cancel out. Another thing we note is that the phasor diagrams, well, they're symmetric about the center. So here you can see on either side we get a square, and on either side we get that straight line. And so as a sanity check, when we're drawing our phasor diagrams, we should expect that they're symmetric. Okay, and so considering the secondary maxima now, again, the secondary maxima, they sit on the minima of the previous slit's interference pattern. So in the previous slit interference pattern, we had a minima over here. And so we should expect now that there's a maxima on top of that, a secondary maxima rather. And so what we should expect is that the phasor diagrams should be exactly the same as the phasor diagrams for the minima in the previous slit pattern, which is consistent. We expect a triangle. But now that we have 4 slits, we should expect that the 4th slit is left over as excess. And that 4th slit is what contributes to the secondary maximum. And similarly, for the second secondary maximum, we should expect that same pattern, the upside down triangle, for a 240 degrees phase difference. But now that we have 4 slits, we have 1 left over. And this contributes to the secondary maximum. Excellent. So give the 5-slit interference pattern a go now. I'll show you what it looks like. It looks like this. So once again, the central maximum and the first order maximum, they're all the same. They'll always look like this, as we explained earlier. And then the first minimum is, if we sub in to k on n lambda, we get 1/5 of a wavelength of path difference, or 72 degrees phase difference between each adjacent phasor, to which we get this nice pentagon, which cancels out to 0. Rotating a bit further, we get 144 degrees of relative phase difference, which gives us a pentagram. and then rotating even further to 216 degrees, we get a pentagram in the other direction, and then rotating even further, we get a pentagon in the other direction, and so on. Once again, it's symmetric about the center, and once again, because we have an odd number of slits, we should not expect that a path difference of half a wavelength should yield destructive interference. In fact, what we should expect is that it yields a secondary maximum. What we see once again with the secondary maximum is that we get the phasor diagram of the previous slit's destructive minima, but with one phasor left over that contributes to the actual secondary maximum itself. Okay, give the 6-slit interference pattern a go. I'll reveal what it looks like. Looks like this. Once again, maxima exactly the same. And what we notice is that in this column here, we'll always get sort of the n-sided polygon associated with that n number of slits. And so before we got a pentagon, now we get a hexagon. We also had a square, we had a triangle. That's always going to be the case. But now we sort of notice these repeats. We've definitely seen this triangle before. We've definitely seen these alternating phasors before as well. And so what we get is that we sort of get repeats of the previous slits phasor diagrams. This was never the case when we just had 3 and 5 slits. When we had 3 slits, we sort of had these unique patterns. We've never seen a triangle prior to this. Similar for n equals 5, we get the pentagon and pentagram. We've never seen that prior to this. The only ones that we've seen before are the central maxima, but critically the minima are always going to be unique patterns for 3 and 5. So what's so different between the numbers 3 and 5 versus 6? Well, hopefully you have realized that 6 is a composite number. It is not a prime number. And so critically 6 is made up of the prime factors 2 and 3. And so what you should expect is that its destructive minima are an integer multiple of cycles of the phasor diagrams of each of the prime factors. So for instance, here, this second minimum here, what this is it's 2 cycles of the 3-slit destructive minimum. This middle pattern here is 3 cycles of the 2-slit destructive minimum. So the alternating phasors 3 times. So every time you've got a slit number that is a composite number, its destructive minima are going to be the n-sided polygons as usual, and then everything in between is going to be sort of multiple cycles of each prime factor's phasor diagrams, because you can go around the triangle any number of times you want and you'll still end up with destructive interference. Same for the double slit. Okay, and that's it. So I hope you found that cool, but now you have to get back to the high school stuff. So until I have another mental awakening, I'll catch you next time.